Okay, here we go. Lesson 4.4. All right, so this is called the isosceles triangle theorem. Well, I like this class. Four objectives today. All right, recall from last class to show that parts are congruent, right? To show that either two angles or two sides are congruent, show that they're part of two different triangles, show that the two triangles are congruent by the five silver bullets. We don't have the five, we have three. We'll get two more next class. And then lastly, claim CPCTC. To show that two sides are parallel or two segments are parallel, right? Show they're part of two different triangles. Show the two triangles are congruent, right? Claim CPCTC for two special angles, sorry. The two angles that are alternate interior angles, either AB or DC, right? AB or DC, those are alternate interior angles. And then because they're congruent, therefore the sides are parallel. All right. A couple loose ends we got to clean up. First off, we got to clean up those missing two silver bullets. In order to do that, we got to talk about a special kind of triangle, right? Right. We were still missing those two. So before we get to those last two silver bullets next class, we're going to concentrate on one specific triangle, and that one specific triangle is going to be an isosceles triangle. So what makes an isosceles triangle? An isosceles triangle is one, and you should have this already in your notes, is one where two sides are congruent, right? For some reason, this shape always reminds me of Nightmare Before Christmas. It kind of looks like him. Oogie Boogie. All right. Um, cool. Isosceles triangle. So what are we going to do about isosceles triangles today? Well, first off, we're going to name the parts. So in your notes, right, I want you to draw an isosceles triangle, mark the two sides that are congruent, and then I want to label them. This is a definition. They are going to be called the legs of the triangle. Well, that leads an additional side. We're going to call that side the base. Now, the number one mistake the kids make when they do this is they assume incorrectly that the base is always the bottom of the triangle. The base is not, for an isosceles triangle, always the bottom of the triangle. It's the third side of the triangle. The two sides of the triangle that are congruent are called the legs, and the third side is called the base. And yes, many times it is the bottom, but not always. Talk about the angles. The angle that is included between the two legs, two angles in the side between, two sides and the angle in between, called the included angle. For an isosceles triangle is called the vertex angle. And yes, this particular one's at the top, but no, the vertex angle does not have to be at the top, right? Which leaves the other two angles, those are next to the bases, so we call them base angles. So I will be referring to those vocabulary words throughout this lesson today, and anytime I talk about an isosceles triangle. All right, just remember, if those are all the names, right? Remember that the angles opposite the legs are called the base angles. So opposite a leg is a base angle, not a vertex. Opposite a leg is a base angle, not a vertex, right? The second but here is that remember, this whole triangle could be turned on its side. So for the kids that always say the base angle is the bottom, well, there's an example right here where the base is on the right side, not the bottom. And the vertex is not always at the top. Now it's on the bottom left. Or if I turn it the other way, it would look like this. So just make sure you understand this. All right, let's prove something. All right. I'm going to prove that if you have an isosceles triangle, that the base angles are congruent. Remember base angles, right, are the angles that are, why is this not drawing? Base angles are the sides that are opposite. I said that backwards. Base angles are the angles that are opposite the two congruent sides, right? Okay. So that's our given. Um, let's see. If that's our given, and we're trying to prove that angle B is congruent to angle C, well, we have that initial problem. Remember that initial problem, right? The initial problem is that to show that two angles are congruent, we need to show that they're part of two different triangles, right? Part of two different triangles. Got that? Right? That's the path we're going to take. We're going to show that they're part of two different triangles. Then we're going to claim the two triangles are congruent by SSS, SAS, or ASA, and then claim CPCTC. All right, let's do this. Um, I only got one triangle. Hmm. Oh, I know what to do. Let's make two triangles. So we want to keep angle B and angle C part of two different triangles. So when I split this up, right, I'm going to split it up in the following manner, right? I don't want to go through B or C. Now I have two options. Either I can go to the middle of BC or I could split this angle into half. And I'll just say the proof works either way. I'm just going to choose to split the angle up in half. In other words, I'm going to make an angle bisector. So I'm going to go through A, cut it in half, and go to point D. All right? And that's just a basic construction. All right, so the consequence of that is I made two congruent angles, that angle and that angle. Are you yelling at the screen? I hope so, because we got a reflexive property, right? So I got the reflexive property. Therefore, the two triangles are congruent by SAS. And that's how the proof ends, right? All right. What the heck were we proving? Let's think about what we were trying to do. We were trying to prove that if you have an isosceles triangle, that the base angles are congruent, and we just did that. So that is, in fact, that is how the proof ends, and that is theorem 4.1, or called the isosceles triangle theorem, that says that if you have an isosceles triangle, then the blue part, the base angles are congruent, right? So I'll pause the video and write that down, please. Okay. Do you remember what corollaries were? Corollaries were derived from a single theorem, right? They are theorems in and of themselves. We don't call them theories, we call them corollaries because they derive from one theorem, right? If you think about a tree as being geometry, the limbs being the theorems, the leaves would be the corollaries. All right. They usually don't have names. Sometimes they do, but most of the time they're just called corollary one, corollary two, corollary three of the theorem that they come from. So we're gonna get a bunch of these. So a bunch of corollaries from the isosceles triangle theorem. Remember what the isosceles triangle theorem stated? It says that if you have an isosceles triangle, the blue part, right, the angles, the base angles are congruent. All right. Here's our first corollary. Think about this. If I had an equilateral triangle, well, what makes it equilateral? Well, that means all the sides are congruent. Well, if we cover up the bottom, right? If we cover up the bottom tick mark right here, then that's an isosceles triangle, and therefore that would make the two base angles congruent. So that would be those two angles, right? Okay, and then I usually say tilt your head to the left, and now imagine that this one isn't there anymore. It's still there, but just imagine it's not. Well, then we still have an isosceles triangle, and the two base angles would be congruent, and that would be, let's see, that would be this one. See how that works? So if I erase all my scribble, let's see what we got. Well, we got an equiangular triangle now. So it turns out that equilateral triangles are, in fact, equiangular triangles. Equilateral triangles are actually equiangular triangles. Hey, by the way, that was a proof. So that's corollary 1 to theorem 4.1 that says that if you are equilateral, you are also equiangular. All right, that was pretty easy to remember. All right, moving on. Think about this. Let's see. I have an equilateral triangle, right? Can I say something because I now know it's equiangular? Right? Well, yes, if it's equiangular, that means all the angles are congruent to each other. That means either one could be substituted in for any of them. I'm going to substitute angle A for angle B and angle C, so therefore I would get that statement right there. I know that some of the interior angles of triangle add up to 180. And since all the angles are the same, then they're all angle A or they're all angle B or they're all angle C. That means there's three angle A's. And if I divide 180 by 3, I get 60. All right. So this is another way of saying that, to remember that n minus 2 times 180, right? It's another way of saying this. So this is corollary to theorem 4.1 that says that if you're equilateral, then your angles are equal to 60. Why? Because it's equiangular. There's three of them. They add up to 180. All right, moving on. This one's really important. So think about this. If I have an isosceles triangle, well, I clearly have a vertex. The vertex is the included angle between the two congruent sides. If I make an angle bisector, right? I make an angle bisector. We have proven by CP/CTC, right? Because the two triangles congruent, reflexive property, right? That the bottom sides must also be congruent. Well, if that's the case, then that red dotted line, right, would mean that those two angles are congruent by CPCTC as well too. So that's two angles that form a line, therefore they must be right angles. Cool. Well, that would make the red line a perpendicular bisector. It's perpendicular because the angle's 90. It's a bisector because it cuts the bottom in half. So not only is it an angle bisector, it's a perpendicular bisector. That's corollary 3. Now, this only happens when you make an angle bisector through the vertex. So the bisector of the vertex of an isosceles triangle is perpendicular to the bottom, called the base, right, at its midpoint. Okay, so we haven't really done anything using these, so let's use some of these to answer some questions. All right, first one's a proof. So I need to prove that AB is congruent to AC. So let's see, what do we have here? I don't have anything except that the two angles are congruent. I suspiciously think this might make it isosceles. I just don't know. In fact, that's what we're trying to prove. We're trying to prove that two of the angles are congruent. That's an isosceles triangle. So let's see if we can do that. All right. As always, to show that two sides are congruent, show they're part of two different triangles, and they're not. They're part of one triangle. So let's make it two triangles, right? Let's do this process right here. So once again, I could go to the middle, or I could make an angle bisector. I just always choose to make an angle bisector for this particular proof. It would work the other way around as well. So I'm going to make an angle bisector to angle A. That means that I have two congruent angles. Ooh, I do have a reflexive property, right? But that would be AAS, right? I don't have an AAS yet, right? Ooh, I'm kind of giving away some secrets, right? So I have that. Now here's the problem. The problem is I don't have an AAS. I have an ASA, I have an SAS, I have an SSS, and I don't have any of that yet. So what can we do? What can we do? What can we do? We have that previous theorem, right? That says that if you have angle ADB, let's see, ADB is why is it congruent to ADC? Why? Well, we're going to reach way back to 2 chapters ago that said that if you have two angles of one triangle congruent to two angles of the other one, then the third angles are congruent. This was a corollary as well, too. This was called the third angle theorem or corollary. So therefore, they're congruent and they're on a straight line, so therefore they're 90. And now I have my ASA, right? All right, so this would be a very challenging proof because it asks you to remember something you did 2 chapters ago, but it's fair play. All right, so what do we actually prove? We prove that if you have two angles of a triangle congruent, then it's isosceles, right? So that would be the converse to the isosceles triangle theorem. So that's actually theorem 4-2, a converse to the isosceles triangle. So this time, if you can show that two angles are congruent, then you can claim that they're isosceles. Why? Because the angles, right, that are congruent have opposite sides, and this shows that the opposite sides are congruent. Okay? So that is what the theorem basically says, that if you have two angles that are congruent to a triangle, then that makes it isosceles. Could be equilateral as well too. We don't know. All right. So where are we going after this? Let's see. Where are we going after this? We have some corollaries to this. All right. So the first corollary says this. I'm not proving this one. If you are equiangular, you are also equilateral. This would be the converse to that first corollary to 4-1, right? So if you are equiangular, then you're also equilateral. Now, I'm not proving this one because they're going to ask you to prove this tonight for homework. Okay. So how do you use all this? Let's see. We'll go easy, medium, challenging. So here's an easy one. So it says find the value of x. Well, x is, well, here. Let's see. What else do we have? Oh, it's isosceles triangle. So if it's an isosceles triangle, right? If it's isosceles triangle, then we know that the base angles are equal. So if one is 50, then the other one is 50. Cool. Let's see. Oh yeah, triangle has 180 degrees. So if I add those two 50s, I get 100. Subtract them from 180, I get 80 degrees. So that's a fairly straightforward and easy one. All right, let's do a kind of a medium one. All right, to make it more challenging, we'll throw some variable expressions. Step number one, what is this? Well, by the converse, we know if two angles are congruent, that makes it isosceles. Then that means that the sides opposite the two congruent angles are the two sides that are equal to each other. So all we need to do is set those two things equal to each other and solve them. Subtract 2x from both sides, add 8, divide by 3. Therefore, x is 15. All right. So hopefully you can see this pretty good. This doesn't project very well in class, but it shows up here pretty good. All right, let's see if we can figure out each one of these one by one. Ooh, look, I got an isosceles triangle right here. The two congruent tick marks, that means the base angles are equal. Well, then that means that's 51. The second one, let's see. If this is 43 and it's an isosceles triangle, it is. Then the other side is 43. 43 and 43 are 86. Subtract 86 from 180, and you get 94. I'm going to do these very quickly. You can pause and try to figure it out yourself. Or the next one might be the most challenging one. A little bit hard to see, but if I ignore this part of the triangle right here, if I ignore that part right there, I can see that the top triangle is isosceles. If it's isosceles, well, that means that's 40, right? But let's see, this angle right here is 90, right? So if that's 90, and you just said that that side is 40, well, that leaves 50 on the other side, which means 50 and 50 is 180. 50 and 50 is 100, and subtract that from 180, you do in fact get 80 degrees. Did that make sense? Right? Let me get rid of those drawings and show you that again. Right? So that's 40 because it's isosceles. That's a right angle, so that's 90. 90 minus 40 is 50. It's also isosceles, so that's 50. 50 plus 50 is 100. Subtract that from 180, it's 80. Okay. Um, I need the eraser. There we go. Okay, let's do the next one. Oh, look, the triangle on the right is isosceles, so therefore that side's 58. 58 and 58 is 116. 116 from 180 is 64. Look, vertical angles, which means that's 64. It's isosceles, so the other side is, or the other angle is 64. 64 and 64 is 128. 128 from 180 is 52. 52 degrees. Last two are pretty straightforward. Let's see if that side's 9, then that side must be 9. No math involved there. And the last one, think of the big triangle first. If I have the big triangle, look, the big triangle is isosceles, right? If you have an isosceles triangle, right? Isosceles triangle, and the vertex angle is bisected. Look, it's being bisected because those two angles are equal. Then what does it do to the bottom? It cuts it in half. So if one side is 12, the other side is also 12. You could also get it by the two triangles are congruent because of SAS. Either one works. Okay. So that is how the lesson ends. All right. Yeah, I usually will have some kids have some questions about this one. Do your best. Come see me in the hallway or see me before or after school with questions or send me an email. I'd be happy to help you. And with that, I will end the class.